Hello everyone and welcome back. So what we have here is yet another one of these beam examples. And what you can see is we have a beam that's like T-shaped beam. And it's going to have a bending stress at point K of 2600 psi. And wants us to figure out, well, if there's a bending stress of 2600 psi at that point, what is the bending moment acting about the z centroidal axis? And then also using that information, determine the bending stress at point H, whether that's in tension or compression. Okay, so just remember this whole thing. That's going to be helpful. The equation's helpful, and also the centroid equation. Okay, let's make sure I give it all to you. Yep, sum ya over sum a. There you go. Okay, two equations. I wrote them down for you to help you out, and now I send you off to the wolves. Go forth. Try the problem. See if you can solve it on your own. If you can't, come back here. It's a video. You can pause. You can just. There's no judgment. I'm just a video, but you come on back after you've done it and see if you did it right, or just to bask in your own magnificence. Okay, so 3, 2, 1, and you're back. So let's try it out together. Now, as always, we gotta do some tables. Why? Because we gotta figure out where that centroid is. I'm gonna say that my reference axis is gonna be the bottom of my inverted T shape. Luckily for me, there's only two shapes. There's that bottom rectangle and the stem. And they both have the same area. And they're just the same shapes, just one's horizontal, one's vertical. For a rectangle, its centroid is directly in the middle, so from that I can figure out where their centroid is located from that bottom axis. I'm measuring from here. I have to measure from the same place for both of them. And then I multiply that together, the area times the distance from the bottom axis to their centroid. And then using this, I can actually calculate the centroid, which will come out to be 0.75 inches. 0.75 inches from the bottom. Okay, not bad, not bad. The next thing to do is we're going to have to calculate the moment of inertia. Now, once again, this is base height cubed over 12. So for that bottom flange, it's got a very, very small height. For the stem, it's got a very, very large height. If you're not certain which one is the height, think about it this way. The base is always parallel to the axis that you're rotating around, while the height is perpendicular to that axis. That's always been good for me. Remember that there's tables and all kinds of stuff to help you out here. You can also look up online if you forget the equation for the moment of inertia for any particular shape. So I calculate that, but neither of those is on the centroid. And so what I have to do then is I have to say, okay, neither of you is on the centroid, and therefore I have to use my parallel axis theorem to calculate the overall moment of inertia for each of them. So it's going to be the moment of inertia around their centroid plus d squared a. So I do that. I calculate the distance, which since they're the same size, the centroid was right in the middle, and so it's the same distance to both of them. The sign doesn't matter, and their areas were the same, so these two values are the same. And then I finally add the moment of inertia about their own centroid to this correction term to figure out what the total moment of inertia is for both of them. And then I add them. Also, if I had for some reason a gap, like a hole in the middle of a rectangle, this would have a negative moment of inertia when you add it all together. Okay, now let's try to calculate that bending moment. So at point K, that's 2.5 inches from the bottom, which is going to be 1.75 inches from our centroid. We have this shape. This is 2.5. And we know that this is 0.75, that centroid, and that's where y goes from. So we had to figure out what y was. We just solved for it right here. We know what the bending stress is. It's 2600 psi, and it's positive. So we can then determine the bending moment magnitude. Simply going to be rearranging this. So we multiply our stress over, or we divide by stress and divide by moment on both sides, and then we invert. And what do we get? Well, we get that it's negative 84.2 pound-foot. Negative 84.2 pound-foot. And then if we want to calculate the bending stress at point H, which is at the very, very bottom, well, that's going to be 0.75 inches away from my centroid. We can use the flexure formula to calculate that. We know what the bending stress is, and we can plug it in there. Now, if you got confused because this is pound-foot right here, and this is pound, I've changed it back to pound-inch. Why? Because everything else is in inches. It just makes more sense in that case. And since it is negative, it's going to be compression. Okay, oh, I went too far. So that's it. We use our flexure formula, we use the equations for moment of inertia, and we use our tables to help us calculate the centroid moment of inertia. And we're done. This formula is pretty simple to use. It's not a terrible equation. So I hope it helps you. I hope these problems are going to assist you. We're going to do a couple more, a little more difficult problems, and we'll move on from here. So thank you for listening, and I'll see you all next time. Bye-bye.